Yeah, great. Okay. I love this picture so much. Okay. So in the previous subcarrier wave, we discussed that we want to turn around the culture of tuning out alerts. I want to continue this conversation and give an introductory talk on how to make our alerts more reliable and actionable to ensure that we are confident enough to respond to alerts, along with initiating an incident without the strenuous work of distinguish noise from real threats. So bear with me. I know that this is not a fun topic, but it's an important one because incidents can be stressful and costly, which is why we should eliminate as much stress and unknowns as we can prior to it happening by over-preparing ourselves. One of the main benefits of having good alerts in place is that we can intervene issues before they reach to our users. I want us to enter a phase where we will be taking every alert seriously. So I prepared some materials to help support that goal. If you know the story of the boy who cried wolf, this is just a little comic parody of the story. So when we create alerts, we should prioritize them in places that could cost the business more. For example, an alert to monitor the recent bug that prevented the users from checking out when purchasing our services, or monitor any API request quota overage, which can potentially bring down multiple services, or several alerts on the dash task worker cycle, which can render the watch service unusable when the cascading failures manifest themselves all the way to the front end. There should be alerts in different parts of our distributed system. For example, categorize our alerts into front end, back end, hub sub, task worker, task runner, and cron jobs, and label them clearly in the alert name and description. All alerts should be actionable and worth responding to. If the issue can be ignored, it's not important, and there's no need to create alert for it. A good strategy to know whether an alert is necessary is to imagine if you'd be okay responding to the alert in the middle of the night if you're on call. Alerts need to be frequently groomed, adjusted, and tuned. We can either do it during sprints with SRE's participation or whenever we acquire new knowledge, such as adding a new alert at a place with no prior monitoring, but has proven to be more impactful than we anticipated. And we should practice muting alerts during grooming and maintenance to avoid false positives. Oftentimes during adjustment, new data also takes a bit time to regenerate. The cloud resources we use are good at auto-repairing. There may be some alerts that get fired and resolved in seconds. We need to use our judgment to determine if that is too noisy so we can tone it down, or there's a real underlying issue that's causing it to trigger frequently. We don't need a million of alerts that can make maintenance a nightmare. We only need a few quality ones that we actually respond to. Alerts and metrics should be created based on causes, not symptoms. For example, the symptom of our GKE nodes going down for the dash task worker is that our users can't view videos. The cause of the problem is node's health. Therefore, alerts should be prioritized in monitoring the liveness of our pods, and an additional symptom monitoring of the front end processing failure may be supplemental. We learned from our last watch incident that general monitoring of a total number of errors isn't really helpful during triaging. The granularity of alert should ideally be down to a specific log message in a specific component of our system per application. This helps reduce responding time significantly. Using the most recent Google Cloud Network incident, even though it was a universal outage, only the editor was affected. And because the alert was configured by application, if fired within the editor alerting channel. This ensures that other squads don't get disrupted, and our our communication departments craft an accurate message towards our users on the affected product. As our application and teams grow, it's necessary to practice naming convention on alerting channels. We should start off by responding to the most critical alerts. Channel names should clearly indicate the level of severity. They can be further broken down to by environment, application, system, or even personal preferences, like the screenshot here. We can build our alerts by adding performance monitoring or staging monitoring later on when we have less critical alerts to respond to in the production environment. Finally, alerts should have detailed documentation that explains how the alert is configured and the basic steps to resolve the issue. In the future, more extensive RIM books should be written based on previous experiences, so a problem can be mitigated more efficiently before it gets escalated to an incident. So moving on to general implementation. The way I organize alerts is by tiers. The top tier is infrastructure resource, which is managed on the Google Cloud project level. All task worker and cron job related metrics and alerts are under the project ID Castify cluster because our Kubernetes engines live there. Web app related metrics and alerts are under project ID Castify storage because our cloud run service lives there. The project ID Screencastify manages App Engine, which hosts part of our legacy extension backend for user accounts and licensing. So metrics and alerts related to that go under that project. The project structure can be a little confusing right now. I think it would be the best to have each application in the future in its own project that manages its own cloud resource, pubs up subscriptions and topics, GKE task workloads, and so on, like how Castify Edit is set up right now. The second tier is applicational squad. The alerts are filtered to a specific application for the designated squad. The third tier is distributed component or service, whether it's on the front end, back end, or task worker. Again, learning from the last incident, I find that organizing the alerts this way significantly reduce responding time and stress during a time when every minute could cost us money. There's currently no easy way to move around or edit alerts. We need to manually maintain them, but there is an option of using Google Monitoring API labels and monitoring as code to dynamically ingest variables, environment, and project IDs. So if a log name or a log message has been updated or removed, or if an alert needs to be moved from project A to project B, we can configure all of that in the code rather than manually update it on the cloud platform. And this should be our next phase of monitoring implementation. Next, I'm going to go over an effective alert example for Watch. So here is an example of robust alert. It's alert that will fire when the unactive message count in our PubSub component increases by 10 units for a minute. The alert name clearly labels the application and component it's monitoring. It's in the PubSub component for the Watch application. It's an essential part of the whole task worker system because if a large number of undelivered messages accumulated in PubSub task queue, that means started tasks are never completed. They're just pending and triggering frequent retries. We have multiple mechanisms in place to resolve pending tasks. So if the number continues to climb, that's definitely a red flag and should be responded to. Here is a graph of the alert metric using a 6-week time frame. I don't know if anyone can see it, but like if I click, sorry, oh my God. I'm going to open the actual alert. And here is the time frame that you can adjust to 6 weeks. So on average, there is a pattern of some pending tasks within normal range below 1,000. This is the threshold right here. The first large spike was when the last watch incident happened on October 18th. You can see the dates here, where we had a quota overage on the GKE primary node pool, resulting in pods scheduling failure. The second spike was an attempt to improve the retry logic in the dash uploader that caused a temporary outage of the worker. So data from both times was accurate and evidential. This alert has been groomed and adjusted multiple times and now uses rate of change to set the threshold empirically by comparing new data with old data. So this is the Google built-in metric, and granularity is the total number of undelivered pub/sub messages. Although this is not the cause of processing failure, it's a direct reflection of unhealthy pods. As pods go dark and don't bounce back, tasks get stuck in a retry loop and never get completed or acknowledged by pub/sub. That was ultimately what caused multitude of video playing failure on the client side. So every alert looks like this. On the top right, this is where you can adjust the time frame. And as I scroll down, there is a documentation section. For any newly created alert, it should state clearly how the alert is configured. So it should have a description of how the alert is configured and basic steps to triage. This is a basic run book I wrote for this alert, and any additional notes. So Watch has a pretty solid set of rules, and I did whatever I can to make them as complete as possible. But for some alerts, steps to mitigate the issue are still being investigated and gathered. It's going to take team effort and time to collect that knowledge and write them down. For now, a few basic steps is enough to get a head start in triaging, but as we grow, the documentation should also involve to ensure that it's the most effective solution. It also means that we don't have to memorize countless steps for something that has already been resolved in the past. We also use this metric to horizontally autoscale our GKE nodes. So we have another alert in place that fires when the metric absence is detected. So Watch alone has about 19 alerts. Some are disabled, but their metrics are used as references. As we grow and start implementing alerts for other applications, the volume alerts will grow inevitably. With the current scale of our SRE team, the time involved in creating and tuning an alert has become more difficult to maintain. That begs the question of how do we continue managing our alerts efficiently? We currently have two options. One is to place an SRE with each squad and have the SRE manage the alerts. Two is to have squads own the alerting rules with the central SRE's help. So essentially, the central SRE can create the most critical alerts and work with the squad on new and existing alerts in the long term. This is a decision that will require senior management's involvement, but either way, we will need to start giving squad engineers permission on Google Cloud Platform so they can get more involved. I hope that with practice, our engineers will have the confidence to declare and participate in incidents. I made a recording on how to declare an incident on Slack, and I will also share this deck after the meeting. So more resources on alert implementation specifics will also be shared. When we have more extensive run books, the ultimate goal is to automate fixing the error out of existence. I know this is a lot of information to soak in, but with more reliable alerts in place, I'm confident that we'll detect incidents early, mitigate and resolve the problems before they reach to our users. Because we want to eliminate noise and only have alerts we respond to. Lastly, I want to open a discussion on the tool Sentry. How do we fully utilize Sentry and make its alerts more meaningful? Sentry is an error reporting tool that can be set up on the front end, back end, and Kubernetes engine. We currently only have it implemented on the front end. The alerts can be configured to monitor a specific error or a total volume of handled or unhandled errors. Sentry monitors a different set of problems. Unlike Google Cloud monitoring, Sentry won't give us any warnings on infrastructure health or outage, but it will tell us what type of error it is and potentially where the error is generated. I say potential because the stack trace uses Webpack, a built main.js file, and our front ends are minified, which makes tracing the error a little bit difficult. Due to the volume of errors and the fact that we had experimented a project in the past to investigate and fix those errors, engineers have developed alert fatigue, and it was determined that it was not the best usage of engineering time. I mean, we're paying for Sentry, so how do we maximize its value? This doesn't have to be solved in this meeting, but I think it's a good opportunity to collect some feedback from the engineers who actually use the tool. And this is from me. That's it. Thank you for listening.
Thank you for preparing and sharing this presentation, Lou. This was definitely a lot of information, but this is great and useful material.